Today's mini lecture will be about KMAPs or Karnaugh maps, and in order for KMAPs to be introduced, obviously Boolean algebra and expressions and simplification of functions using Boolean algebra and properties of Boolean algebra has to be already introduced, so that in other words, KMAPs is actually another way of simplifying a circuit or a function instead of using Boolean algebra, usually because KMAP is more straightforward and easier to use after the person or the engineer gets the hang of it. Uh, so that's what we'll be talking about today. However, before I proceed, obviously, I will give a simple example of Boolean algebra 1 here, and transition, hopefully try to transition smoothly from Boolean expression or Boolean algebra to um, KMAPs. So if we start with this truth table, which is with inputs something's not right with the pen. I'm still not used to using these pens. It's working now. So we have the three inputs x1, x2, and x3. Obviously in the truth table you need to do all combinations. So you get 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1, which obviously represent the midterms M0, M1, M2, M3, M4, M5, M6, and M7. And there's just really row 0, row 1, row 2, row 3, etc. It's like counting in binary 0, 1, 2, 3, because if you convert it into decimal, then it's 0, 1, 2, 3. And since the topic is not about minterms and max terms, however, it's probably okay to just mention it. Minterms is usually when we look at the function output where it's a 1. We draw the K-maps for, or the Boolean algebra. But when it comes to max terms, it's usually when we get the expression using the function expression using the expression where the function is 0. So, but at the end it's all the same. The resulting function will be the same. So both maxims and minterms. But it's beyond the scope of this lecture. So for this mini lecture, we're just going to focus on KMAP. However, we need to know the minterms because the minterms will be drawn in our KMAP. So if we give an example, this is just an example function output of 1 for minterm 0, 0 here, 1, then you get 0 here, and then let's say 1, 1, 1, 0. So in other words, whenever you have x bar, x1 bar, x2 bar, x3 bar, you have the function is equal to a 1. And when we say bar, it just means that your inputs are, the input is 0, inverted. So what the function would be here is as follows. It's as easy as reading your function with inputs 1, 2, 3. And it's equal to wherever the function is a 1, just like I said earlier. And now this will give us x1 bar, x2 bar, and x3 bar. And again, we're using minterms here, so the expression for maximum will be different. However, the final result should be the same. So it's like saying this can be solved in two different ways, at least two different ways. Now we have the x1 bar, x2 bar, x3 bar obviously came from the zeros here, and then we get the second one here, which for minterm 2. So this is minterm 0. So now for minterm 2 we get x1 bar, x2, and x3 bar, and this is minterm 2. And then if I scroll over a little bit to go to minterm 4, so my minterm 4 would be x1, x2 bar, x3 bar. So that's my minterm 4. And then my minterm 5 is x1, x2 bar, x3, and my midterm 6, which will be my final one, it's x1, x2, x3 bar. So my midterm 6. Now this is the full, you can say the full-blown function. And now we need to simplify using Boolean algebra. Usually in Boolean algebra it's very simple. We really relate minterms together so that we can find a way to simplify these expressions and get maybe, or obviously we want to get lesser terms, for example lesser terms than we have here, or lesser inputs to each term. And the reason is that the cost of a circuit is really directly proportional to the number of gates and the logic gates, which are obviously the AND gates and the OR gates that you're seeing here. Like these are ANDed together, and this is an OR gate, and the number of inputs, which we call fan in those logic gates. So if we can decrease this as much as possible, then we have obtained a lesser cost circuit. In other words, in reality, we're looking for the minimum cost circuit for a logic function. And KMAP does that, just like Boolean algebra would right now. So if we join M0, maybe I use another color for the simplification. So if you combine M0 and M2, you can see there's some variables here that are in common, and they're precisely x1 bar and x3 bar. What happens here is x2 bar ORed with x2. This becomes the 1 due to a property in Boolean algebra that you should be aware of at this time. Basically 0 ORed with a 1 or 1 ORed with a 0 gives you a 1 all the time. Now we've taken these into account. Now we're remaining with the other M4, M5, M6, but we can easily see M4 and M6 can be joined together using x1 and x2 bar, sorry, x3 bar. And what's in common here? These are the ones. Then you get x2 again and x2 bar, and this is a 1. Now we're left with M5. The other good thing about Boolean algebra or properties is that you can replicate an expression, because there's an expression, for example, x plus x gives you an x. So we can reuse 4 with a 5 here, and we do that because we want so that we can simplify it further. The thing is, if we couldn't join M5 with any other minterm, then we have to write the M5 as is. But now we can see here M4 and M5 can be combined to create a new expression, and that will give us literally x1 and x2 bar, now x3 bar ORed with x3. This is a 1. So we can see we're already simplifying it, and it has become this expression with this expression and this expression. Now we're not done yet until we actually finish simplifying. We can see there's x3 bar here that are in common for these two expressions, 1 and 2. So we join these, x1, x3, x3 bar, and then x1 bar ORed with x1. Same thing, this becomes a 1, so we can actually see that this has simplified dramatically. And we're remaining with this, which we cannot join anything else. So it'll be x1. Oh, if we want, we can. However, there will be no point for it. So it has to go by itself. So the final answer would be x3 bar ORed with x1, x2 bar. And this is your final answer. And you can easily see that it is a much more simplified expression with what we have here in the light blue. Obviously, we do not need to count the amount of logic gates and the inputs to actually prove that this is more costly than the simplified one, because there's much more difference. For example, you can see 2 inputs here, and you can see well, if you want to count the inverter, assuming that the inverter is already already provided to a circuit, we can see 2 inputs here and only one here that has no logic gate combined with it, unless this actually will be ORed with that output. However, here you can see there's a bunch of inputs and logic gates. So it's obvious. So this would be called the minimum cost expression or circuit for that function. Now that I have discussed this, in KMAPs will actually do something exactly like that without going through any Boolean algebra. However, keep in mind that because of the Boolean algebra, the KMAP is feasible. Now, before I go into this, I want to transition, before we transition into KMAP, it's useful to see why KMAP exists to begin with. And the idea behind this, I'll use another color here. The idea behind this is that we want to see some sort of a pattern here. For example, generally speaking, what input out of these three inputs, what input or inputs actually do not change when others change? In other words, let's look at x3. I can already see this, so that's why I'm actually using x3 here as an example. Let's look at x3, x1. Let's look at x1, x2. Now x1, x2 is 0, 0, and then the other one is 0, 1, and then the other one is 1, 0, and the other is 1, 1. These four different combinations where these functions is a 1 actually tells me it's all combinations for two variables. So it's 0, 0, 0, 1, 1, 0, 1, 1. All variables. In other words, regardless of what x1 and x2 are, x3 you can easily see that x3 is always a 0. So this is something we can observe in the truth table. So in other words, these four min terms are combined in a way to produce its own version of its own terms. And you can actually see this in the Boolean algebra we did. What we did here was M0, M2, M3, and M6. They were actually being combined here and then combined another time here to create your X3, right? So basically what was remaining was M5, and that's exactly what I'm seeing in the truth table. M5 we haven't accounted for yet. So what do we do here? We actually want to see another pattern here that would help us see some sort of a relationship in combining pairs. I can easily see here that M5 and M4 has something in common here. For example, regardless of what X3 is, 1 and 2, X1 is 1, X2 is 0. You can see it easily here. So if X1, in other words, I can say this differently. If X1 is 1 and X2 is 0, regardless of X3, the value of X3, then the function will be a 1. And you can see here that's exactly what we did. We joined M4 and M5 after replicating M4. Now, as a homework, look deeper into this relationship, because actually this relationship, the grouping relationship, is what brought us to what will bring us to K-mapping. And that's exactly what I'll be talking about next. So keep in mind the grouping that we just discussed. In K-mapping, it's very similar to truth table. It just takes it makes the truth table look a bit different. So if we looked at two variable K-map, what happens in this case? You only have 4 different combinations, and that's obvious because you have 2 bits to the power 2. You get 4 different combinations. That's what we're seeing here. Now, in these 2 different combinations, we have minterm 0, minterm 1, minterm 2, minterm 3, which is really equal to 4 different combinations. Now, this is truth table. How does the K-map look? It's reordered in a way. Again, remember the grouping, and you'll see it soon. It's grouped in a way where your first input is your columns, your second input is your rows. So x1 can either be 0 or a 1, x2 can either be a 0 or a 1. Now, if input x1 is 0 and input x2 is 0, that's a 0, 0, that represents minterm 0, and 0, 1 represents your minterm 1, minterm 2, and minterm 3. And the reason why I'm writing this, so far I'm not even actually given an example with a function. Well, like where the function, just like in this truth table here, we had functions. One, I'm just giving you how we represent the look of KMAP. That's for a two variable KMAP. Obviously, with a three variable KMAP, you would need 2 to the power 3 different combinations, which is 8 combinations. And what would that mean? It's double the size of the two variable KMAP, which would mean you're putting two variable KMAPs together. We'll get to that shortly. However, keep in mind why we're doing this. We're trying to, if you notice here, we're trying to put these minterms in a way that we can group them together. Hence, just as a clue and a hint from what I was talking about, there was something to do with combining these variables together. But in a truth table, you can see they were separated. It wasn't clear. So KMAP allowed us to put these ones, the ones we can say here, the function ones, in a way that they're going to be grouped together. This is the simplest form of KMAP, the two variable. So M0, M1, M2, M3 looks exactly like this. Now just look at it basically in a Boolean algebra way yet, instead of talking directly about KMAP. What would M2 be as an example? M2 is this one. It's really with an X1 and X2 bar. So X1, X2 bar would be your M2, or with M3, and it's X1, X2, and X2. So basically, this is again, the example is M2 or with M1, M3. Now, if we want to simplify this, we take X1 as your common factor here, and X2 or with X2, just like we did earlier, we end up with X1. So you can see that we can simplify it to a nice one input variable. So that's if you want it to be either M2 and M3. Now what do you say if you want to join these things together and have them like this instead? What you do is just like how we're doing with what changes and what not. Just like earlier we were saying, X3 was changing in these M4 and M5 groups. So it's X1 ended with X2 bar, which is this expression here. So X3 wasn't included because X3 was changing. So same thing with KMAP. Because because X2 was changing. You see the row here, X2 is a 0 for this one. If we join them, I'm saying, if we join them together, because X2 is a 0 and X2 here is a 1, it's changing. So the answer would really just be the variable that's not changing, which is X1, and that's what the answer is. And this is what KMAP is all about. And we didn't have to do any of this. Now we can go to three variable KMAP so you'd see it very clearly, and I'll show it to you shortly. So what we do here is with three variable KMAP, like I said earlier, you have 3 inputs, so you end up with 8 different combinations. And obviously we're going to start doing X1, X2, X3 with all combinations, which is 0, 0, 1, 0, 0, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and finally 1, 1, 1 for midterm 0, midterm 1, midterm 2, midterm 3, midterm 4, midterm 5, midterm 6, and midterm 7. And then if we give a function here for this as the example as 0, 1, 0, 1, 0, 1, 0, 1, now we know the ones are here, and that's where we're gonna focus to group together in our KMAP, such as this, but in 3 variable. So that, like I said earlier, the 3 variable KMAP would require two of those 2 variable KMAPs joined together in a way that will make sense. So how we know it from the 2 variable KMAP, we have obviously here the box like that with 4 cells. Now that we have 8 cells, because it's 8 different combinations, right? So because we have that, we will join another one next to it, and you'll soon see why it's next to it, not below it, because that's how the inputs are placed. And we have 8 cells, you can see. So you can easily see why, because we want to have 3 variables, so we can only have 2 columns here and 2 rows here and 4 columns here. So we end up with 0, 0 for x1, x2, all combinations again. Now please notice here that I did not write 0, 0, 0, 1, 1, 0, 1, 1, as it would make sense. The reason is, again, I'm not going to go too much deeply into this, is the fact that adjacent cells, that we're trying to group them together, we want them to not differ from more than one bit. For example, if we wrote this like the conventional way of how we write things, like 0, 0, like in this case 0, 0, 0, 1, 1, 0, 1, 1, we see that these two adjacent cells differ in two bits together, and we don't want that. And when we do K-mapping, we just want it to differ by one bit. Hence, we had to switch between these two. Now, and x3, obviously, because it's just one bit, it's either 0 or 1. So because we join these things together like this, we can see how the midterms will be written. 0, 0, 0 is midterm 0, obviously, and 0, 0, 1 is midterm 1, 0, 1, 0 is midterm 2, 0, 1, 1 is midterm 3, 1, 1, 0 is obviously midterm 6. So you see here the flip. So that's one thing you have to be careful when you're solving these problems. 1, 1, 1 is midterm 7, 1, 0, 0 is midterm 4, and then 1, 0, 1 is midterm 5. So now you have all the midterms. Now the thing we need to do is put where the function is a 1. At midterm 1 is a 1, at midterm 3 is a 1, at midterm 5 is a 1, at midterm 7 is a 1. So now we have all these one laid out. Now here I was just giving you a general example where I'm joining these together. And we assumed like these were where the ones were. Now in midterm 3, sorry, with 3 variable KMAP, like I said earlier, we need to join as many ones as possible. Actually, if I haven't said that, that's what I should be saying right now, is that we need to join as many ones as possible. And it's very obvious by just looking at this example. If you took only m5, you know that this variable will be, this term will be x1, x2 bar, x3. So that's 3 input, and that's one term. And if you keep doing this, you'll have their own 3 input or whatnot terms, and they're all going to be ORed together. But if you join, and which is allowed, you can join 2, 4, 8, etc. together. You can actually join the whole thing if you have all filled. What will happen in this case, I'll change the color. What will happen in this case, the expression will be literally the most simplified. So what does this actually mean? A quick way to do this, and like I said earlier, it's at the beginning the student has to get used to it. However, once the person or the student gets used to doing these problems, it's much easier than solving Boolean algebra expressions. So for here we see whatever is not changing would be the final, will be in the final function. So the function here, which has 3 inputs, the only thing that's not changing is x3, obviously, because the whole row has x3 equals 1. No 1 is shared with x3 not, or x3 bar. But you can see here x1 is changing here. It's a 0 in these two ones and a 1 for these two ones. And obviously same thing for x2. So they're not included. So the answer would really be x3. And you can see that's very simplified. And we did this without minimum cost circuit, and we did this without using Boolean algebra properties like we did earlier. So that's why I brought you from solving Boolean algebra here, so that you see that it is very useful tool. Now that was the 3 variable. Now if you want to talk about the 4 variables, which is one of the most popular ones, you have, let's say, x1, change colors. If you have x1, x2, x3, x4, still I'm not used to this pen, x4, and you do all combinations 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1, 0, 1, 0, 0. So we do all combinations 0, 1, 0, 1. So it's like repetitive work, and then you get 0, 1, 1. Now these are all filled. We're gonna go with to our x1 input, and you can see x1 input. The far left here doesn't change as fast. You can see this actually, it's very useful for the 5 variable KMAP to note that this expression, half of it will be a 0, another half will be a 1. So it only changes twice. So now we'll do the same thing we did earlier, but with ones for this one. And you can see it's a lot of inputs, and that's because for variable, KMAP means would mean to the power 4, which is 16 different combinations. So minterm 0, minterm, we should stop at minterm 15. That's what we're trying to do here. Minterm 4, minterm 5, minterm 6, minterm 7, minterm 8, minterm 9, minterm 10, minterm 11, minterm 12, minterm 13, minterm 14, minterm 15. So you have all 15 combinations. Now let's give the output function for this. I don't need to do the lines. You have 0, 0 for example. There's just an example. 0, 0, 1, 1. And then I go 0, 0, 0, 0, 0, 1, 1, 1, 0, 1, 0, 0. Now obviously the next step will be to actually do the KMAP for it. And now we have, just to refresh your memory, it used to be for 2 KMAP, x1, x2, that's the only inputs we had, so 4 cells for 4 different combinations, and then we had to double that into 8 cells for 3 variable x1, x2, x3. Now what would obviously make sense, you need an x4 here and double this. So because this is 8 cells, those 8 different combinations, now the 4 variable KMAP will have twice as that, which is 16 cells, and it will look like you're putting 2 of these, one on top of each other, and I'll just show you now. It'll be a bigger square than the 2 variable one. It's a good habit to go center, center, so that try your best to make it look even. So now you have 4 by 4, so it's 16 cell or 16 different outputs for an x1, x2, x3, x4 variable. And obviously here we have all combinations just like we had earlier, and we have to remember you switch these, so it's not 1 0 1 1, it's 1 1 1 0. Same thing for this one. Now we have all combinations, and obviously we have to put the minterms. So 0 0 0 0, which is this one, is midterm 0, and then you get m1, and then you get m3, and then you get m2, and then you get m, and so on. I'll just write this as fast as possible. M7, and then M6, and then M12, M13, M15, M14, M8, M9, M11, M12. Now that you have those, we place these ones in their respective cells. So M2 will have a 1, and M3 will have a 1. Then you have 9, 10, 11, 13. 9, 11, there's a 10 here, obviously I missed. 10, 9, 10, 11, and 13. So now I have all these ones, and obviously the remaining cells will have a 0 in them. So we care here, because we're working with minterms, we care here about the ones in this KMAP. Now what does that mean? Well, before we proceed, because it got bigger, like earlier here we can see x1 is here, x1 bar is here, x2 bar is here, x1 is bar, x2 bar is here. We didn't write anything to differentiate these, but here it's a good exercise to actually write where x3 falls, because there's a lot of cells. So we see this first bit, which is the x3 bit. It doesn't, it's x3 is here, and we don't write the x3 bar because we know the remaining ones would be x3 bar. And here it's x1 because x1 here is 1, and here's x1 bar, and x2 will be actually these two cells where it's equals to 1. Obviously, with these two remaining ones will be with these two remaining of the x2 bar, and these two rows will be your x4. This is very important because when you're actually doing the minimum cost expression, you will use these to guide you do it faster with less error possible of errors. So now let's combine our ones. So as I said earlier, we're trying to as much as possible, we are trying to combine as many ones as possible that are beside each other. In this case, we can see these two are adjacent to one another, and their expression would be, now I'll try to go a little slower, but here with an x1 we see that both 1 lies with x1, just like how we did the 3 variable. X1 doesn't change. So in other words, these both of the ones that are grouped together here, they are both in x1. None of them fall in x1 bar, hence we write this x1. Now we can see that these two can be joined like that, and these two can be joined like that. But that's someone who hasn't done this before would think so. However, there's another thing I have to explain, which makes it actually a better expression, because if you join these together, you'll end up with something similar. Like here would have an x1. Oh, actually this is not done here because this was x1 joined together, and then you should go with every variable. What happens with x2? x2 is changing, so this one falls in x2, this one falls in x3 bar, x2 bar, and x3 you can see they both fall in x3 bar, which is this row. So x3 bar should be there, and x4 they both fall in x4, so there's an x4. And the reason why I noticed that I should have continued is when I looked at it, it looked like a one variable. Usually to obtain one variable, we need more than these two joined together. Like in this case, there were 4 ones adjacent. We got one variable here, so it doesn't make sense that you don't have more than one input in this 4 variable, which is 2 joined. So that's exactly what I wanted to talk about here. If you join these two separately like this, you'll end up with at least this many inputs, right? If not exact, it would be exact because you get x1, and then x3 and x2 bar. X4 is not there. So same thing. There is something that is very important to actually add to this, is that we're looking at this as a two-plane. So if you look at this as a sheet of paper and you want to fold it like this to the edges, these edges actually here, they meet. And when they meet, it means they are adjacent. So they will end up looking like this. For example, the two edges, they meet here. So they meet here, the two edges, and now they're actually adjacent, and which means you can group. In other words, these two ones can be grouped with these two ones, and you end up with only one group you have to worry about, which is equal to, let's start with x1. Does x1 change? I can see 2 of these ones fall in x1, 2 of these ones fall in x1 bar, so we don't include x1. Now looking at x2, I can obviously see it's an x2 bar, and that is because x2 bar are these, x2 is these 2 columns. However, x2 bar are these 2 columns, and all 4 ones fall in x2 bar, so that's included for sure. Now we look at x3. It's obvious that x3 is in it. Only x3, it's not changing. And looking at x4, x4 is changing because these 2 ones fall in x4, and this is an x2, this is an x4 bar. I'll pause it for a second here. Thanks. Alright, I had a little chat there going on. Anyways, the function would be here, or with this one. So your final answer in the four variables will be x2, x1, x2, x3, and x4, and the answer will be obviously x2 bar, x3, ORed with the top one, which is x1, x3 bar, x4. So that's actually your most simplified expression, and you can see we haven't used any Boolean properties to do this. Now there's also, before I go to a five variable, which actually the five variable I was going to give more for an assignment. However, it's a good thing to actually remind you here. Earlier when we started, we said we could use this, we could replicate a midterm. There's nothing, it's the same thing in KMAP. We can do something similar. So if I give you this as an example, here, try to do this fast. We get 0 0 0 1 1 1 1 0 0 0 0 1 1 1 1 0 x1 x2 x3 x4, and let's say your inputs are as follows: 1 1. Your function output will be all ones here, then 0 0 0 0 0 0, and let's use, okay, here is x3. I'll write it down for you because I'm used to it, but I'm not sure if maybe it's useful to keep showing it for now. And here's x4 and here's x2. Now we want to group these things together. Now let's start grouping like this. We can, the best one we can see is this one. We have all 8, and that's like music when it comes to KMAP. That is because, and good music actually, and that is because when you join this many, you're left with only 2 to worry about. However, for now you can see the expression is the least amount of terms you can use when it comes to that, instead of joining them 2s or 4s or this row. So what does this actually give you? This actually gives you a very nice x3, and that's it, because that's the only variable that doesn't change. x2 changes, x4 changes, x1 changes, x3 doesn't. So that whole bunch of ones gives you an x3. Now why I'm giving you this example? Because earlier I was joining 2 and nothing was reused. So these ones were grouped together, these ones were grouped together, and none of them were actually reused. And that's why I'm giving you this example, to remind you that in Boolean algebra and stuff we could use minterms and replicate. And that's one of the reasons why, if you did just that, it's correct, but it's not the minimum cost expression, because this will be equal to, let's say, x1 is not changing, x2 is changing, so x3 bar and x4. That's this variable. But if you reuse, I'll use another color for this one. Does this look normal? I guess I don't like that color, so I'll use something else. Let's use this green. If we reuse these two ones that are here with that one, the expression is obviously changed to x1, and x3 is not there anymore because x3 bar, because x3 is here and it's over there. x4 change. So you can see there's 2 inputs now instead of 3. So we don't use this term, and therefore the function here would be equal to x3 or with x1 and x4, ended with x4. So this is basically just what I wanted to mention here. It's very important that we group these ones as efficiently as possible, like together. If we don't do that, then the KMAP purpose is we don't use KMAP as we should. Now for the 5 variable, like I said, most of it will be done in homework, but I'll just guide you a little bit here. So going back to one of my favorite scholars, would be 5 variable KMAP would be as follows. I'm not gonna write the whole truth table because it's huge. It's not that huge, but it's tedious. That's is one of the reasons why usually we don't go beyond 5 variable KMAP. We usually use CAD tools and stuff and other techniques using which is beyond the scope of this lecture. It's prime implicants and essential prime implicants. But for now, what we need to know for 5 KMAP will be, you need 32. just like we did earlier, we would combine the previous KMAP and we multiply by 2. So for a variable KMAP which has 16 cells or different combinations, for 32 obviously you need 2 of those. And how do you do this? You do not join them together, and that the secret that lies with this is because, like I said, if we took this as your x5 here, let's assuming this was a 5 variable here, add another one so I don't have to write it. As you see, there's half of this variable here is 0 and the other half would be 1. Same thing with 5 variable. In other words, a whole 4 variable KMAP will be your x5 being a 0, and the other whole 16 cell KMAP will be your x5 being a 1. So you can see here we're only using 4 variables, and obviously that's not the case for 5 variable. We need a 5th one. Like I said, and I'll show you in a second, that the 5th one, just like how we did earlier, here would be your x1, here would be x4, here would be x2, here would be x3. Now where's your x5? Your x5 is actually this whole cell, this whole 4 variable KMAP where x5 equals 0. Now you do it again for an x5 equals 1, and hence it's a 32 cell or different combinations. So same thing here. And now you have, however, it's for x5 equals 1. Now, but one thing it's very important that we note here. Now what's going on? What really is going because this is a two-plane screen, we had to put them side to side, but in reality they are really 3D shapes. So for example, the first KMAP will look like this, and the other one's right behind it. Like so, for example. And the reason why we're saying this is because the ones can be grouped together in a different way than we did before, which is, let's say as an example here, you're grouping these. Let's say we have ones here, and now let's say you want to group things together. Now remember, these two are of one on top of each other, hence 1 1 1 1 here, 1 1 1 1 here can actually be grouped as one expression. So this you have to know when you solve the problem. So this can be grouped as one expression, okay? And you do that as a homework, but it is grouped as one expression. And these ones obviously can be grouped together like so, and this like so. The thing is, it means that when you group these two together like this on top of each other, the variable x5, which is here and here, they're changing. So you won't include it. That's the whole idea behind this. In this case, these groups will be in x5 1. Anyways, the idea is that you have the function here as follows, with 5 variables. Your final answer will become like this, and if you solve it, you should be able to get that. Now this is your final answer. Now of course it is the minimum. Actually, this is the minimum. This is the minimum cost expression. Obviously it's a little more complex looking than these ones, and obviously this one, and obviously the 3 variable here, and that is obvious because this is less number of variables. So this is the best we can do when we have this many input variables in a circuit. I hope this helps, and good luck on your midterm, and until next time, thank you.